Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure to have Professor Benedito Aguiar Neto with us, and I hope the recording works well. Professor Neto comes from the University of Campina Grande in Brazil. He's spending some time at the Institute of Technology at University of Washington in Tacoma until June, you said, right? Yeah. So maybe we'll have opportunities to see you again. Yeah. And he's going to be talking. You did a PhD at the TU Berlin some time ago.
Yeah, 20 years ago.
And been working with speech processing and related areas for a long time, and it's a pleasure having you here. So
thank you. It's a pleasure to be here. I thank you for the invitation from Enrico Malvar, and I am going to present my current where's the the last one here?
Where the 75% to the left of it, that little corner. See where it says 75%. Here, say this little thing here.
Ah, okay. Yeah. Too small. I am a user from 98. Yeah, I have to change. Das ist mein Doris computer. Yeah, I'm going to present my current research interest, and I will present some principle about and some results about acoustic analysis and modeling of pathological voice. This work is, by this working, we have another, my team, our team is, we have two students, one student and two Professor Josiana from University of Campina Grande and Professor Mena Kamupa from University of Washington, Tacoma, Institute of Technology. As the main topics of my presentation, we have an introduction. I'm going to present in the introduction the goal, the main focus, and the main reasons for the research. And after that, the basis for the acoustic modeling, in especial the speech production process, model for speech production, the analysis of normal and disordered voice, and modeling of disordered voice. And I will explain the used database and methods, and the feature extraction, the classification process, and some results, evaluation, performance, and the conclusion. The goal of the research is to specify and modeling the most significant acoustic characteristic of disordered voice to build a basis for development of effective methods for discriminating between normal and pathological voice. As main reasons for the research, I can say that disorders in voice are common and presently have been increasing due to unhealthy habits and vocal abuse. As well, there is a great range of disease which cause modification of the speech. Speech processing is particularly interesting for acoustic voice analysis due to simplicity and the non-invasive nature of the measurement procedure. It is very important to consider that this method is a non-invasive method. The main topics of the study is acoustic analysis and acoustic modeling. The acoustic analysis provide the analysis of acoustic features of disordered voice to characterize the most significant acoustic features of pathological voice. And the acoustic modeling provides a statistical model for the acoustic observation of the pathological voice for pattern classification. The degree of the reliability and effectiveness of the discriminating process depends on the appropriate acoustic feature extraction. Our research aims to specify and evaluating the most significant acoustic features for characterize vocal fold edema. We are concentrate to this disease, vocal fold edema. For that purpose, it will be used a parametric modeling approach based on the resonant structure of the human speech production mechanism and a non-parametric modeling approach related to human auditory perception system. For the acoustic modeling of a pathological voice, three subjects are very important to be considered. The process of the speech production, the digital model for speech signal, and the feature estimation for the statistical model of speech. This is this block diagram that shows us the human speech production system. Yeah? The vocal fold vibration produces the excitation for the vocal tract, represented here by concatenated acoustic tubes representing the laryngeal, the nasal, and oral cavities. And it is very important to be considered the radiation effects too by the nose and the mouth. In the first step, our research, we are using the classical articulatory model for speech production. The model is based on as purpose for Rabin and Schaefer. Yeah. The model is based on the acoustic theory. The excitation features are separated from vocal tract and radiation features. Vocal tract and radiation features are represented by a time-varying linear system. This is very known by the Rabin Schaefer book. And we have here the excitation generator and a time-varying linear system and speech output. The complete model includes the vocal tract response and the effects of the sound radiation at the lips and nose. We have two transfer functions representing these features here. By the complete model using linear prediction analysis, it can be combined glottal pulse, radiation effect, and vocal tract all together as a single transfer function. And here we have this is a single transfer function as the product of these three transfer function. A of z is the predictor error filter. The predictor error filter, A of z, is given as this equation here, A of z, 1 minus P of z, where P P of Z is the linear predictor, or the P defined as combination of previous samples. Based on the linear model of speech production, we can say that the voice signal is produced by, as a result of glottal pulses, or a signal like a noise, this is the excitation, filtered by the vocal tract. The key to modeling disordered voice is understand the change of the acoustic features involved by the excitation and resonance effects. There are different kinds of pathologies which affect the vocal fold or other components of the vibratory system, producing a more irregular vibration pattern, or affect components of the resonating system appearing as modification of the morphology of the vocal tract shape that produce irregularities on the spectral properties. Typical effects occurring in disordered voice are, for example, fundamental frequency variation, the amplitude irregularities, subharmonious component, turbulence noise, voice breaks, and vocal tremor. Our study is mainly focused on organic pathologies affecting the vocal folds. This class of disordered voice may include pathology such as polyps, edemas, nodules, paralysis of the vocal folds, etc. This picture shows normal vocal fold in two stages, the open and closed. And here we can see a complete cycle of the vibratory movement from this stage, the opened vocal fold, to the closed, completely closed vocal fold, and in between the intermediate stages. This is the complete cycle of the vibratory movement. What now is a vocal fold with disease, a pathological vocal fold, in that case with nodules. These nodules provoke change in the elasticity, causing an incomplete closure of the vocal folds. That means the vocal fold cannot produce the glottal pulse and regular glottal pulse because of these nodules. Here's a typical waveform for normal voice and pathological voice of sustained phonation of the vowel R and same millisecond voice samples. Here is the normal voice, and here is the pathological voice. We can see the clearly additional noise in the speech, and then change in the pitch period too. Here this picture shows the variation of the pitch period for normal and pathological voice for sustained A. Here is the normal voice, and here is for pathological voice. We can see quite variation for the pitch period. The pitch period was analyzed or measured for each 10 milliseconds.
So what algorithm do you use to compute that pitch period?
For
It was by hand or with a program?
On program, yeah. This is MDVP from Key Elemetrics. We use, and MATLAB too. We have MATLAB too. This is but in that case here we will use the MDVP program from Key Elemetrics.
But how do we know that this is the truth as opposed to an artifact of the measurement? The program may not be right.
Yeah, I cannot know exactly if this factor. We can just compare with the normal voice in many different cases for many different files, speech files. But this is
you could also annotate it by hand, trying to.
No by hand. This is
you
automatic.
could do it just to
Yeah.
make sure that
Yeah.
indeed that's the case as opposed to
Yeah.
because there is no.
Waveforms you showed seem to be relatively easy cases, right, where a reasonable pitch algorithm wouldn't have much difficulty.
Yeah, this is very, very difficult to find. And now this variation of the format for normal and pathological voice for the sustained R. Oh, this is a very big, very high confusion for the first format for the pathological voice in sustained R.
So what is the explanation for that?
Yeah, this is because of the increase of the mass of the vocal fold and the decrease for the elasticity of the vocal fold. The vocal fold cannot vibrate regularly, and
But the first format typically has to do with the shape of the mouth.
The trick is that because it doesn't close, then it doesn't produce as many harmonics.
mid harmonics, yeah.
So you're missing the harmonics that would show the format. So your ability to find it goes down because you didn't have the excitation to drive it.
Yes, yes, that's right.
So the format is there. It's just more difficult to find.
Plus, it may actually be varying as well because there's some interactions, right? Because what you're measuring, as I said, is the cascade of the three transfer functions. So, and something happened to one of them.
Yeah, this is the classical model. Yeah. So far, we are in just the classical model to analyze. This is the first step for the research, but.
And how do you compute the format there? Was done by hand or by some other program?
But some program. Yeah. This is the same program
But
to
those
use.
programs, computing pitch is not easy always. Computing
Yeah.
formats is even more difficult.
More difficult, yeah.
So basically, you're making a point of the limitations of the classical model.
Yes.
And you try to compute the format every 10 milliseconds.
No, the formats we have used 256 spectral components. This is I cannot see exactly in time.
What is the sample?
25 kilohertz.
You guess by the number of points.
Yeah. 10 milliseconds. Yeah, 10 milliseconds. Yeah, okay. This is the second format, too. Here, the spectrum for normal voice, the sustained R. You can see the position very clearly, the position for the formats. But here now, by the pathological voice, this is a completely changed of the position of the formants.
But the oscillations may have to do with just the estimation algorithm. There seems to be like F1, more or less. It's not as high of a bandwidth, I mean as small bandwidth,
Yeah.
but it is there. It's just that when the bandwidth goes down, it's more difficult to estimate.
Yeah. In general, those measures are limited to variation in either fundamental frequency or peak amplitude of the glottal wave. There are static measures, long-term measures. However, static measures are not correlated to perceptual dimension of the voice quality. And due to the dynamic nature of the vocal tract speech is dynamic or time varying, and the modeling needs to consider the explicit temporal dependencies of the pathological voice, and the estimation of the features has to be based on statistical short-time analysis. Yeah? It is usually assumed that the statistical speech signal properties change relatively slowly in short-time segments, for example, 10 to 20 milliseconds. The approaches based on the speech production model have to represent the behavior of the nonlinearities introduced by the pathology itself. An important requirement is imposed. The model, the pathological voice, both the vocal tract and excitation source information have to be included. You can see that more important this is the excitation, but this is we think the both excitation and information, vocal tract information, the excitation source have to be included. Previous works have demonstrated the use of short-time Cepstral analysis as a useful and very reliable tool for that purpose. The main advantage of the Cepstral analysis to provide a parametric acoustic feature extraction. This approach has an intrinsic reduction of the dimensionality of the feature vector. And two parametric approaches based on speech production model were used. The linear predictive code, the LPC analysis, the classical LPC analysis, and LPC-based Cepstral analysis. And in addition, one non-parametric Cepstral analysis based on the human auditory perception system was used too, the Mel-Frequency Cepstral coefficient. The Cepstral is defined as the inverse Fourier transform of the logarithm of the power spectral density of the signal. This allows to separate the two components, excitation and vocal tract information. The Cepstral coefficient can be calculated recursively from the LPC coefficient, as proposed of Fourier in 1981. This method provides a logarithm relationship between the real and the perceived frequency scales, the Mel scales. The Mel-Frequency Cepstral coefficients are calculated by means of this equation, the log energy estimation, and the with window and window, triangular windows. Yeah. By the computing of the M frequency, M is the number of the Mel bands in the Mel scale in S of key, given by this equation here, where the W key of K of K is the triangular weighting windows associated to the Mel scales. a common model for the relationship between the frequency in male and linear scales given by this equation here. This is very known, and use it, this relationship here, proposed of Rabina and Ruan. Yeah, the acoustic modeling provides the statistical modeling for the acoustic observation of the feature vector X. It provides a way of calculating the probability of observing a feature vector sequence X given a uterus W. A pathological voice detection can then be regarded as computing the probability of observance a sequence of feature vector xk, given a related model patho k for normal and pathological voice, just as here. Yeah? And the related model patho k can be represented as a hidden Markov model. HMM can be understood as a generator of vector sequences. It is a finite state machine that changes its state at each time unit. This is a 4-stage Markov chain, and at each time t and state j, a vector y is generated with probability density b. The transition from state QEI to state QJ is also probabilistic and is governed by this discrete transition probability A. That is, we need just B and A to modeling the speech. This is the probability to pass from state 1 to 3 to 2 to 4 to stay in stage 1, etc. Does the set of the parameter AB of the HMM provide a reasonable means for characterizing the behavior and interrelationship between different states of the speech production processing? Considering the initial probability μ at t equals 0, start of the process, the set of parameters given by these three parameters, just these three parameters, A, B, and B. Therefore, the model patho k is given by patho k equal A, B, and me. And based on the maximal likelihood principle to model parameter set, patho k, A, B, and me are estimated so that the likelihood of the training data is maximized. Therefore, the probability of vector sequence X given reference model, this reference model here, is calculated as the product of the transition probability A and the output probability density B, summing over all any possible state sequence of B. As database, we have employed a database distributed by the company K-Elemetrics that includes more than 1,400 normal and pathological voice samples. We have selected cases with edemas in the vocal folds from 44 patients, 33 women and 11 men. The normal voice database is composed of 53 people, 21 male and 32 female. This is our database, used database. About the acoustic feature extraction, it is assumed that the speech signal can be considered stationary during an interval of 10 milliseconds. This is our supposition. Yeah? This allows define a short time window of speed to extraction the parameters. The feature vectors are computed for every 10 millisecond frame of the speech samples over a dynamic input standard vol R. For the classification process, we are not using HMM yet. We are using just the vector quantization technique that is associated with a distortion measurement, just vector quantization. Our purpose now is to find the most important acoustic feature, and HMM should be the next step for as classification process, classification technique. The vector quantization is carried out individually for each feature using just voice under vocal fold edema. Thus, different vector quantization trained distance classifiers are obtained by the discrimination process. The vector quantization was trained with 20 voice signals under vocal fold edema. In the test phase, we used 5-3 normal voice, 24 signal under vocal folds edema, and 23 speech signal of speakers affected by other pathologies as nodules, polyps, cysts, and paralysis. But by the training, you have used just vocal fold edema. For the evaluation of performance, we used these 4 parameters for evaluations parameters: the correct acceptance, the correct rejection, the false acceptance, and false rejection. And we defined the specificity representing the likelihood that the pathology is rejected when it is absent. The sensitivity representing the likelihood that the pathology is detected when it is present. And the efficiency representing the correct classification of a given class when that is present. Now some results about this using this method, 3 methods for feature extraction: LPC, Cepstral coefficient, and Mel-Frequency coefficient. By the training method, we said we used just speech sample of vocal fold edema. And in that case, by the test phase, we used speech samples of vocal fold edema, not all the 23, just the 50%, and from other, by the training phase, we didn't use, you didn't use all the vocal fold edema files, just 50%. But the test phase, you use all the speech sample of vocal fold edema and from other pathology, just nodules, cysts, and paralysis. Yeah. And here we have, by the LPC, we have a very high correct rejection and very low false acceptance. Thus produce a specificity very high, and sensitivity 33. And by the Mel-Frequency coefficient, that is very interesting, we have a very low correct rejection and very high false acceptance. But very interesting, the sensitivity is higher than LPC. You can say that this low correct rejection means that there is a confusion in separating the vocal fold pathology and others pathology. The Mel-Frequency coefficient are not able to separating the vocal fold pathology and of others pathology. LPC is better. This is the best here. If you use different and similar pathologies in the discriminations process. And you can see here the distortion behavior with LPC method for normal, edema, and other pathology. We have here a very good discrimination between normal voice and others pathology and edema pathology. But we have a big dispersion in this class here for normal voice. Now we have in the training phase just retrained the vector quantization just with speech samples of vocal idiom, and in the test phase we use normal speech and vocal fold idiom. This is very interesting now. By LPC we got lower correct acceptance and sensitivity and lower sensitivity. And by Mel-Frequency coefficient we have a higher correct acceptance in comparison to the result of LPC and the sensitivity too. That means the Mel-Frequency coefficients are better than LPC in separating the vocal fold idiom from normal voice. But it's not good to separate, it's not able to separate between similar pathology like nodules, cystos, and paralysis of vocal folds. In that case here, we have lower dispersion for the normal voice here. And here we can see a good separation between normal voice and vocal fold pathology, but not to others pathology. Between others pathology, this is not good, produce not good results yet. We have here two correlated publications about this work, about this research, and in Spain in September, and in Boston by the International Symposium of Bioinformatics and Bioengineering in October 2007. And another work are preparing, and I hope new results or better results can be used by use of HMM classifiers, for example. And as conclusion for the research now is we are concerned in researching the most significant acoustic feature to model pathological voice. LPC method is the best in separating vocal fold edema of other pathologies. It's noted that Mel-Cepstral coefficients are very good to detect the presence of pathology. However, these coefficients are not efficient in discriminating distinct pathologies. In addition, the Mel-Cepstral coefficients are better than other methods in representing the behavior difference of the pathological signal relating to normal case. That is all. I thank you for your attention.
I have a quick question. When you're talking about those probabilities,
Yeah.
you always have a trade-off between false alarm and false rejection.
False rejection.
Depending on how you set the cell sizes for the vector quantizing, right?
Yeah.
So I imagine you already tried to set those in such a way that you had a reasonable trade-off, but no matter what, you still have this problem that you
Yeah.
presented.
Yeah. That's right. Yeah.
So even if you try to, because you can always make them too big, and then you say everything is pathological, or you make them too small, and very, very little would be pathological, right? But then in the case where you said where you're trying to discriminate from one pathology to the other,
Mm-hmm.
no matter what, it looks like the Mel wouldn't work. Things were just too close together.
Too close together. Too
There's no
close
way to
together.
design
Yeah.
such that you
Yeah.
can-
I think you can be able, if you use research, you find search another methods based on more in the excitation of the model, the classical model for the speech production. And I told we speak about that with Alex tomorrow. And one way is to find a method to noise estimation. Yeah, by the excitation, a pathological voice has a very strong noise, additional noise. Not the noise natural to the speak production. It's an additional noise. And if you have a very good method to detection this noise, this is another feature, acoustic feature, to use by the classification process.
Because one disadvantage of the LPC is that it puts together spectral characteristics of
Yes.
the patient
Yeah. This is the idea. Yeah, this is the idea to separate. We will try to use not just one characteristic vector, but many vectors. Maybe one more direct, more for the excitation features, and another for the spectral envelope of the speech, and another for the altogether. We don't know yet, but we are trying to find how should be the best characteristic vector to modeling the pathological voice. Our purpose now is to find the most important or most representative characteristic features. We don't, because of this reason, we are using just vector quantization in the first step. Yeah, we know that the HMM is a better classification process for the classification, but this is not important now. This is the first step, the next step. In the next step, we will be, for example, HMM. Yeah.
So I forgot whether you mentioned this. Are you using static Cepstral only, or also delta and delta?
No, static. These are results for static, but we have.
To me, from the graph that you showed, there is a lot of variation.
Yeah.
Regions where there shouldn't be.
It's better. The delta estimation, delta Cepstral estimation is better. We have this result now, but we prepared a paper for ICASP. ICASP is, I don't know, is approved or no, but this is using the delta Cepstral estimation. But yeah.
How in general this pathology is diagnosed today by the doctors? How early they can detect the presence of that edema? And from this perspective, I believe it's more important to see how sensitive this is in the early stages, because as early as it is diagnosed, especially with this non-invasive method. So in that database, those are all already completely diagnosed, fully blown pathological cases.
Yeah. In that time, the physician are using just laryngoscopy. Yeah. And another acoustic procedures based on long-term analysis. We don't know if I am sure you can say I am sure that those methods are not in use now. We hope that we can, with very good, we can get very good results to building a system to detect the pathology automatically through the acoustic analysis. This is very important to say that you wanted to say that laryngoscopies don't should be used anymore. Yeah, this is for the physician to hear that is this causes a very big impact. Yeah, no laryngoscopies, but yeah. This is should be an auxiliary tools for the physician for using together with laryngoscopy. Yeah, this is our mind about that, about this result of the research. But the main, this is very important, is to say that this is a non-invasive method. And laryngoscopy causes pain, it is uncomfortable.
In general, it can be extremely powerful tool for screening. So you go to a quick checkup with your physician into screening, and there is some probability above certain threshold, and then your physician sends you to confirm the diagnosis for laryngoscopy.
Yeah.
In general, these type of classifiers usually are tuned using ROC or receiver operating characteristics curves.
Yeah.
Then you basically vary, let's say, the quantization size or any other parameter. You build the curves and find the maximum optimal value.
Yeah. The threshold, the optimal threshold. Yeah, we do that. We did that. I have, for example, it's hidden the slide here. It is the rock ROC curve. Yeah.
Okay, thank you very much.
Thank you.